Hey there and welcome. Today we're going to be demystifying something called ridge regression. It's one of those fundamental tools that helps fix one of the most frustrating problems in machine learning. You build a model, it looks absolutely perfect during training, and then it just completely falls flat on new data. Let's dive in.
So picture this. You've just spent all of this time building a predictive model. You run it on your training data and the accuracy is amazing, like almost perfect. You're feeling pretty good about it. But the second you show it some new, real-world data it has never seen before, it all falls apart. So what on earth is going on?
Well, there's a name for that problem, and it's a classic pitfall in machine learning: overfitting. Your model didn't actually learn the real underlying patterns in your data. Nope, it just memorized the training set, noise and all.
Okay, so before we jump to the solution, we really need to understand the problem itself. Let's take a closer look at what's actually happening inside a model when it starts to overfit.
You know, an overfit model has a few really clear symptoms. For one, it starts giving way too much importance to certain features, leading to these ridiculously large coefficients that basically just amplify noise. Then, the model becomes super unstable, especially when your features are highly correlated with each other. That's a problem we call multicollinearity. And the final result? A model that's a genius in practice but fails the final exam.
So, how do we fix this whole mess? Well, say hello to ridge regression. It's a really elegant, surprisingly simple tweak to standard linear regression that helps bring our overexcited, overachieving model back down to earth. To really get what ridge does, you gotta remember where it comes from. A standard, ordinary linear regression model has one single goal: to minimize the difference between its predictions and the actual values. That's it. Its only job is to get as close as possible on the training data, no matter what it takes.
And this is where the magic happens. Ridge regression starts with that exact same goal, but it adds a new, crucial rule to the game, this penalty term right here. It basically tells the model, look, I still want you to be accurate, but I also need you to keep your coefficients from getting out of control. And that right there is the secret sauce.
The best way to think about this penalty term is like a leash. A normal linear model is kind of like an overeager puppy, just chasing every single data point it sees, including all the random noise. Ridge regression puts a leash on that puppy. It lets it explore the general trend of the data, but it stops it from going completely wild and getting lost.
And here's a fun little fact for you. The name ridge isn't random at all. On a mathematical level, that penalty we just added creates a constraint that actually looks like a ridge. Forcing the model solution to lie on this ridge is what stabilizes everything and prevents that instability we talked about from multicollinearity. Pretty cool, right?
Now, that little Greek letter you see, lambda, is probably the most important part of this whole thing. You can think of it as the dial we get to turn. It controls just how tight that leash on our model really is.
Choosing the right lambda is this constant balancing act. If you set lambda to basically 0, well, there's no leash, and you're right back where you started with a high-variance, overfit model. But if you crank lambda way up, the leash becomes way too tight. You pull the coefficients so close to 0 that the model becomes too simple and can't learn anything useful. That's high bias. The whole goal is finding that perfect sweet spot right in the middle.
So here's the really crucial takeaway. We are intentionally adding a little bit of bias. We're telling the model, hey, it's okay if you're not 100% perfect on the training data. We do that so we can drastically reduce its variance, which makes it perform so much better on new data it's never seen before. That's the trade-off. And you know what? It's almost always worth it.
Of course, ridge isn't the only game in town when it comes to this stuff. It has a very famous sibling called lasso regression. They both exist to fight overfitting, but they go about it in really different ways. Okay, so let's break down the key differences. The type of penalty they use is different. Ridge uses what's called an L2 penalty, and lasso uses an L1. Now that might sound technical, but it leads to the biggest difference in how they treat the model's coefficients. Ridge kind of shrinks them all down uniformly, pulling them towards 0. But lasso is much harsher. It can actually force the coefficients of less important features to become exactly 0. And this means their use cases are different. Lasso is fantastic for feature selection, literally getting rid of features, while ridge is your go-to for managing that multicollinearity problem we talked about.
All right, so you've got these two powerful options. When exactly is ridge the right tool for the job? Let's get practical and talk about the playbook.
You should really reach for ridge in 3 key situations. First, use it when you have a pretty strong belief that most, if not all, of your features are actually useful and have some predictive power. Second, when you know you have high multicollinearity, when your features are all tangled up, ridge is fantastic at stabilizing the model. And third, if your main goal is to build a stable, generalizable model and you're not trying to actively eliminate features, Ridge is absolutely the way to go.
All right, let's wrap this all up. What are the big things to remember? At its heart, ridge regression is just good old linear regression with an L2 penalty added on. That penalty is everything. It's what controls overfitting by shrinking down those crazy coefficients. It keeps all your features in the mix, but just reduces their influence. This makes it an incredibly robust tool, especially when you're dealing with multicollinearity. It's a foundational part of any data scientist toolkit, for sure.
Understanding ridge regression is really about getting a feel for that classic bias-variance trade-off. You now have a powerful tool in your belt to tame an out-of-control, overfit model. So the real question is, what's the next source of bias you're going to tackle in your data? Thanks for tuning in.